Welcome. I realize that it's a beautiful day outside, and so you could all be eating lunch outside, and I really appreciate that you're here today to learn something about indoor air chemistry. So thank you for that, and thank you to the AAAS for organizing this lunch. And today you're going to hear a little bit from Dr. Marina Vance, Hugo Destales, and Rich Corsi, who will tell you about indoor air chemistry, and there will be plenty of time for questions. So I'm Barbara Turpin. I'm a professor and the chair of the Department of Environmental Sciences and Engineering at UNC Chapel Hill. I've been studying atmospheric chemistry for about 30 years. Most of that time, I've been studying how outdoor air pollution is transformed by chemistry in between the emissions from sources and human exposures. And I got involved initially in indoor chemistry, but because it turns out that most people, when they're exposed to outdoor air pollution, it happens indoors. So outdoor air pollution penetrates the indoor environment, and that's where people are exposed to it for the most part. So in the process of doing that, what I've learned about the indoor environment is that it is a major location for exposure to chemicals. In part, this is because Americans spend almost 90% of their time indoors. And indoors, people are exposed to chemicals that are brought in from the outside environment and chemicals that are emitted from people's activities, from consumer products, from building materials and furniture. They're also exposed to chemicals that are formed through indoor chemistry. For example, the oxidation of cigarette smoke, where the smoke has sorbed or stuck to all of the surfaces of the building in a smoker's home. And then that oxidation produces new chemicals, some of which are volatile, and people are exposed to those. The indoor environment is also an important location for exposures because the concentrations indoors are often higher than the concentrations outdoors. So when chemicals are emitted indoors, their indoor concentrations are often a factor of 10 higher than the concentrations outdoors. There's limited ventilation, and the emissions are very close to the people who are being exposed to them. Indoor air includes, well, we know about many compounds that are present in indoor air, and those include some things that are not bad for you and some things that are bad for you, and many of which we don't know if they're bad for you or not. It includes things like harmful aldehydes, pesticides, phthalates, flame retardants, bisphenol A, and PFAS compounds, all of which have some health effects. But we expect that there are a lot more chemicals in indoor air than we know about, a lot more chemicals than have been measured. And one reason I think this is true is by looking at the EPA's chemical and product database. It lists over 75,000 chemicals in 15,000 consumer products, most of which don't have any exposure data or toxicological data. We only know about a very small fraction of those chemicals, whether or not we're exposed and what their health effects might be. So having spent a lot of time studying outdoor air, one thing I've come to appreciate about the indoor environment is the influence of surfaces. So if I go home and I spray some perfume in the air or an air freshener, if those compounds stay in the air, then I'm exposed to them right away, but within a couple of hours, they've left the house, right? They've been ventilated away, and I've got some fresh outdoor air coming in. But many compounds don't stay in the air. They partition to surfaces. So that's not at all uncommon. So an example, I live in North Carolina. I try really hard to keep the cockroaches out of my house. It mostly works, right? But if I spray some pesticide in my house on a cockroach, some of that pesticide will volatilize and end up in the air. I'm exposed to that. And it will then partition between the air and all the surfaces in the house. And that includes the building materials, it includes my couch, that foam in my couch, it includes the stuffing in my kids' stuffed animals. And it'll continue to partition in and out. That partitioning to indoor surfaces really dramatically increases the amount of time that chemical is in the indoor environment, the residence time in the environment, and it also increases the opportunity there is for that chemical to react in the indoor environment and produce other things that might then volatilize and we may be exposed to. So the next three speakers will provide specific examples of approaches that we use to research and study indoor air chemistry, specific examples of the kinds of chemistry that happen indoors, and some potential solutions. And so without further ado, I'd like to introduce Dr. Marina Vance. She's an assistant professor and the McLagan Family Faculty Fellow in the Department of Mechanical Engineering at University of Colorado Boulder. In her research, she applies engineering tools to understand and to reduce exposures from everyday activities and from consumer products. She was a principal investigator of a really novel experiment called HOMEChem, and I'm sure she'll be talking about that. In her previous appointment, she was the associate director at Virginia Tech's Center of Sustainable Nanotechnology, and she has a PhD from Virginia Tech. So Nina.
Thank you, Barb, for that wonderful motivation. So, as Professor Turpin mentioned, my name is Marina Vance. I'm an assistant professor at University of Colorado. I go by Nina. And today, I'm here to talk to you about HOMEChem as an example of the types of studies we can do to probe indoor air and we need to do to better understand indoor chemistry. So, let's see. Good. So first, a little bit about my background. So I'm an environmental engineer, even though I'm in a mechanical engineering department. I've been doing air pollution-related research for about 15 years now, since my undergraduate years. So I've been exposed to many different flavors of air pollution, from doing very well-controlled laboratory studies, like using a chamber and known amounts of different pollutants, and going out into the field, going out into the real world and trying to understand what's really going on there. These are two very different facets of air pollution research, and they're both needed. So when I was an undergraduate student, and then I carried on for a few years of consulting as an engineer, I studied odors as environmental pollutants. Then I did a master's degree researching indoor air quality in hospital environments. Then my PhD was about nanotechnology in consumer products. And now, as a faculty member, I'm focused to understanding people's exposure. So how many particles of what kinds are you inhaling and touching during your everyday activities? So as you can see, the field of air quality can span a lot of different sub-areas. I've been exposed to only a few of them, and that just gives you a little bit of a flavor for it. But today I'm here to talk to you about the need for studying indoor air quality and indoor chemistry. So as construction evolves, you can tell that by our homes, right? If you are in a 1960s house versus a brand new house, you can tell that the buildings are getting more airtight. And that's for energy efficiency. That means that our energy consumption is going down, our heating costs and cooling costs are going down, and that can be pretty protective for outdoor air pollution, so you're blocking more air pollution from coming into your house. But if you look at it on the flip side, it's also exposing us further or more to the air pollution that's produced inside, and that's, as Barb mentioned, a little bit less known. When you get into the chemistry, the actual reactions and the mechanisms that happen indoors, the chemistry indoors is likely to be different from what we already know happens outdoors. And that's for these three major reasons, in my opinion, is because we have different sources, different types of air pollution being emitted. We have different types and amounts of surfaces. I mean, look at all the surfaces we have around us right now versus if you were outside. And they're different oxidants. They're the drivers of chemical transformations. Outside, the major oxidant is actually sunlight, and inside is probably going to be other chemicals. So the take-home message here is that chemistry is dynamic and complex, probably in indoor environments. So it needs to be investigated both using those, well-controlled laboratory chamber experiments and in more realistic field studies. So in the past, there have been a few collaborative, large indoor field campaigns. The one I'm going to talk to you about today is definitely not the first one. So some examples include the RIOPA study, and Professor Turpin was actually one of the leaders in that study. So they went to 100 different homes in 3 different cities in the US. They were looking for volatile organic compounds indoors and outdoors, as well as particulate matter, looking at those relationships. This project was funded by the Health Effects Institute. And then another example that I like to point out happened about 10 years later in Europe, funded by the European Union. So they went to 37 different office buildings in 8 countries, and they were looking at similar things. Indoor-outdoor relationships of particulate matter, the composition, volatile organic compounds or VOCs, etc. So one thing that these studies have in common is that they went to as many buildings as possible. So they were trying to do sort of a survey of what exists out there. But they could only focus on a few chemical species of interest because you can't measure everything everywhere. We don't have unlimited resources, right? So their focus was both on the sources indoors of air pollution and the penetration from the outdoor air pollution. Our study that I'll tell you a little bit about today was the opposite of that. So instead, we took one house and we tried to look at as many species, chemical species of interest as we possibly could measure. Our focus was still on indoor sources and penetration from outside, but we also had this more like fundamental chemistry interest on reactions and chemical and physical mechanisms that might be taking place. That we might, if we learn those mechanisms, we might be able to translate that to other situations in other homes. So that's our study. It's called HOMEChem. It stands for House Observations of Microbial and Environmental Chemistry. The study took place last summer, so a little bit over a year ago now. It was, as mentioned, a large collaborative study. We had over 30 state-of-the-art instruments, millions of dollars in instrumentation was involved, over 20 faculty members from different universities in the US and Canada. We had some industrial and governmental partners as well as over 60 researchers on site. And I'd like to acknowledge my co-PI, co-principal investigator in the study. Her name is Dr. Delphine Farmer. She's from Colorado State University in the chemistry department. And you can see the logos of all the universities involved in this study at the bottom there. So as I mentioned, we only used one house for this study, right? And the chosen house was, it's called the UTest House. It's a test house. It's located at the University of Texas at Austin. And the house is a research instrument. It was built for research. Nobody lives in this house. This house was actually purchased over 10 years ago from a federal IGERT education and training grant. And Professor Corsi was one of the leaders, or the leader for that grant, actually. So what we have there, you can see a picture of the house on the bottom, is a 3-bedroom, 2-bathroom manufactured home. But what's really special about this house is that it's been characterized and monitored for over 10 years now. And we can control the ventilation system really well. We have all these measurements of the energy consumption. So it's a house that we already started from a point that we understand really well. And at this point, I'd like to acknowledge Professor Attila Novoselak, who is in charge of really operating, managing, taking care of the house throughout this study. So the house was his research instrument. And I'm going to go through just really quickly I'm going to use this photo from our open house day. Not everybody was there on that day, but whoever was there on that day made it to the picture. And I'm going to use this photo to just highlight some of the types of measurements we made during HOMEChem. So we did measurements of particulate matter physics, and you can see the university logos at the bottom. I won't describe everybody. So that's knowing how many particles are present at any given time, the size of these particles, and how they change, evolve, grow, or get lost to surfaces over time. We also had measurements of particulate matter or aerosol composition, so knowing what the particles are actually made of. Measurements of volatile organic compounds, so I talked about particles, now we're talking about gas phase, air pollutants. We also had measurements of surfaces in the microbiome, so some groups brought their own glass slides or painted surfaces and left them in the house for a month and then brought them back to their labs for analysis. Other groups did swabs on the walls everywhere around the house and then did either chemical or microbiological analysis back in their labs. And finally, we had some groups coming and investigating oxidants using really novel measurement techniques and other trace gas compounds to really understand the drivers for chemistry that's taking place indoors. So the experimental design for the study was pretty novel, so I always like to point it out. I mentioned in the beginning that there's this difference between very controlled laboratory studies and field studies where you go out into the world and just observe what happens. What we have here is somewhat of a hybrid because we have a house that we can't really control. We don't know what's the outdoor pollution that's coming in. We can't control that. But we controlled the activities that we performed inside this house really, really well. So in that case, it's more of a controlled experiment. We still can't control the outcomes. So we try to focus on experiments that involve everyday activities you might all do in your homes, so cooking, cleaning, and also human occupancy and their use of personal care products, because we all, in this room right now, for example, we are changing the chemistry of the air, either by the compounds that we exhale or compounds that are reacting with our skin, things like that. We humans also change the indoor environment, and I don't think it's something that people think about very much. So basically, this gives you an idea of what the experiment was like. We just had a very busy month, and we were performing different experiments every single day. And now we are swimming in data analysis from all of these experiments. So today, I'm just going to leave you with a few bullet points from very preliminary analysis that we've done so far. So one thing that's been proven in other studies already, and we also observed at HOMEChem, is that there were high emissions of particulate matter indoors, so PM or aerosols, especially during cooking. So the use of a stove or any kind of combustion source, but in our case, the use of a propane oven was the main source of ultrafine particles, so the very small ones that are smaller than 100 nanometers in size. The food was the main source of fine particulate matter, so what we usually call PM 2.5. And occupant movements were the main source of coarse particulate matter. So as we move around, there are particles coming off of our clothes and skin shedding and also resuspension from the floors, and that's what we were measuring there. There were many interesting chemical reactions taking place when cleaning activities were involved, and we're still digging through those data to see what that really might mean for human health and indoor chemistry. And also the role of surfaces. They evolve and they change as air pollutants interact with them and as we perform activities indoors. And the other speakers will cover that quite a bit. So my final message to you is that we have done a lot of research on outdoor atmospheric chemistry. We understand air pollution processes pretty well outdoors, but we can't really translate all of that knowledge directly indoors because the processes are as different as I mentioned already in my earlier slides. And yet, indoors is where we live. We're indoors right now. We spend most of our time indoors. So I'd like to finish by thanking and acknowledging my big team of collaborators. Some of the names are mentioned there. And I'd like to mention that we, part of our program that's funded by the Alfred P. Sloan Foundation can be seen in our website, indoorchem.org. We also have a Twitter profile. You can see it there, @indoorchem. We have a lot of blog posts and some news articles and project descriptions. So if you're interested in this topic, I'd like to welcome you to check it out over there. Thanks.
Thank you, Nina. So next we have Hugo Destalets. He's a staff scientist and the deputy leader of the Indoor Environment Group at Lawrence Berkeley National Labs. And his research involves the chemistry of the built environment and urban systems. He's particularly an expert on third-hand smoke, e-cigarettes, and new technologies for energy-efficient buildings. He's done a postdoc both at Caltech and UC Davis, and has a PhD from the University of Buenos Aires. He's a member of the editorial board for the journal Indoor Air, and he's been elected to the Academy of Fellows at the International Society of Indoor Air and Climate. Hugo.
Thanks very much, Barbara, and thanks everyone for being here. Very briefly now, today I'm going to talk about just one relatively narrower aspect of indoor chemistry related with tobacco smoke. If we have tobacco smoke in our buildings, that usually is the dominant pollution source and the most pressing indoor environmental problem, and as we have learned, also an indoor chemistry problem too. So the goal here is to show how indoor chemistry builds into a larger problem and also a larger research endeavor. Before I start, I work, as Barbara mentioned, at the Lawrence Berkeley National Laboratory. We have an indoor environment group there. It's been running for several decades. It's a really very established group. What we do is we study the connections between indoor air quality, health, productivity, and energy efficiency. We are a Department of Energy facility, so clearly energy efficiency is at the center of everything we do, but in buildings we cannot really disconnect it from all the other aspects. So that's why our program is fairly comprehensive. Here you can see from our website some of the topics we are currently studying, and you can definitely go there and learn more about each of them. Today we will be mostly only talking about smoking and perhaps a tiny bit of vaping at the end, because it's very much in the news lately. So like a panoramic view in terms of historic perspective here. It took about half of the 20th century for the Americans and also really around the world to get hooked on smoking. As you see here, the peak is essentially in the 50s and 60s, but then we have been fairly successful in fighting this epidemic for the rest of the 20th century and the current, the beginning of the 21st century, as we see here. So around the turn of the century, this is kind of a medical advice that we had, but also at that time, we already had a good information about the connections between smoking and health. That led to the first Surgeon General report in '64, which was basically a turning point. And then we started focusing on smokers' health, like, for example, with warning labels. Already by the 80s, the focus shifted to the indoor environment and what happens with passive smoking. Our group did, even at that time, important contributions in terms of understanding how to deal with smoking in the indoor environment. Now, if we fast forward to today, I think we have been fairly successful in removing smoke from public places. Now, smoking continues to take place mostly in homes. So our research also now is focused on what's going on in homes. About 16% of adults in the US still are smokers, and that essentially happens in homes and outdoors, of course. So that's how thirdhand smoke came into our discussion. And for the last 10 years, we have introduced this rather new concept of thirdhand smoke by contrast with secondhand smoke, which would be now used only in terms of direct exposure to the fresh smoke as it is produced. Say, as an example, if you walk into a bar where people are currently smoking. Now, in homes, many times exposures are very indirect. Smoking took place maybe a day ago, maybe even weeks ago. Sometimes, you buy a home where the previous owner was a smoker. So the time scales are fairly different, and indoor surfaces play a critical role there, because once the fresh smoke is emitted, good part of it gets removed by ventilation, but a significant fraction actually stays on the surfaces and either is re-emitted at a longer time or it undergoes this indoor chemistry that we're going to talk about today. So going into the chemistry itself, this is a bit of a summary of a lot of the work we have done in our group. We studied the chemistry of nicotine in particular. Nicotine is probably the most important constituent in the smoke in terms of how much is emitted. Every cigarette emits milligrams of nicotine. and how efficient it is as a molecule to stick to surfaces. So we studied the chemistry of that molecule with, for example, on the left here with a compound named nitrous acid, which is also emitted with smoking and other combustion sources. And the reaction is called nitrosation. It doesn't matter, I'm not going to go into the details on the chemistry there, but what's important here is that the byproduct of that reaction is a group of chemicals that are globally called tobacco-specific nitrosamines, and some of which are carcinogenic. So in the table here we show, okay, the names, I don't give you even the full name of the chemicals, just the acronym, NNK, NNA, and NN. These are 3 different molecules, very similar structurally. 2 of them are also present in fresh smoke, and we know they are carcinogenic. In fact, NNK is one of the most carcinogenic chemicals in smoke. The other one, NNA, actually we found on surfaces that we expose in the lab. These are typically not found in the smoke. So this is a compound that is formed on our surfaces, perhaps over long periods of time, that is not present in fresh smoke. So that's purely a third-hand smoke constituent. We also could predict some levels, what to expect on surfaces, and give a very broad range of concentrations. And then, as I'll show later, some of the field work kind of confirmed that estimation. The other chemistry we studied is the reactions of nicotine with ozone. Ozone, as you know, is present in urban smoke. It enters our buildings. It's essentially the main driver of much of the indoor chemistry that we have studied. And what we found with nicotine is that it oxidizes nicotine to form chemicals that I will show in the next slide. And those chemicals many times are present in very tiny particles that we call ultrafine particles that are being produced in these reactions and re-entrained into the air. The figure here shows a measurement we did showing the size distribution of these particles. You see more than half of them are below 100 nanometers. These are particles that go deep into the lungs. Now, in terms of the composition of those particles, don't worry about the chemical structures here. The idea is to see that when you start with nicotine up here on the upper left, you oxidize it, you start seeing a bunch of molecules that look very similar but have between 1 and 3 oxygen atoms. When you put these chemical structures into a model, that gives you a number, and just to simplify here things, that number, which we call asthma hazard index, goes from 0 to 1, gives you an idea of how likely this molecule is to either induce or exacerbate an asthma attack. So nicotine is 0.64, and majority of these compounds, the ones in red there, are higher. That means by oxidizing nicotine, what we are getting are compounds that tend to be more irritating. That's the one thing we learned from our laboratory studies. So by the time we were doing this is a few years ago, other colleagues in California were also involved in other research related with this new field of third-hand smoke. So we got together, we created a consortium. We have been working together for now 8 years and going forward for at least 2 more years. And I'm showing here just so you see the topics that are covered goes everywhere from the chemistry to the various biological studies in vitro, or in animals, in humans, many field measurements, and also we have an effort in terms of dissemination and outreach. We have been obviously producing science on this field, so the publications, as you see here, are growing. This is a field that is growing not just because of the work of this consortium, but also other colleagues that are really contributing great work, particularly in recent years. The other plot on the bottom here shows a little bit how interconnected our consortium is. So we are not just together, each of us doing our own work. We are actually learning from each other and building a very interdisciplinary research. So the first thing we did was a roadmap. That was our first paper in 2011, indicating, okay, where do we want to go in terms of what are the gaps in chemistry, in biology, and in policy. We updated that with a second article in 2017. So if you want to read just one article on third-hand smoke, I would go to this 2017 review paper. I'm very happy to forward you a copy if you're interested. So this slide actually tries to summarize in one slide the work of 8 groups over 8 years, so it's a bit ambitious. This is just to give you the titles of the things the consortium is doing. This is not work my group is necessarily doing, but the consortium. big effort in field measurements. We go out to homes, cars, hotel rooms, even a casino. So we did measurements in many different environments. Our colleagues in San Diego State University are actually leading that work, and very interesting results over there. One thing we found in general is that even in non-smoking environments, you do find nicotine on surfaces. So nicotine is very pervasive, and you can find it even in places that you would imagine is not there. Of course, in smoking environments, it's a lot higher. Tracers and biomarkers. We are interested in finding chemicals that one can measure in the environment, but also in our bodies, and that would allow us to quantify how much we are exposed to this. And particularly if we could differentiate these third-hand exposures from the more, from the second-hand, the exposure to the fresh smoke. Many biological studies, for example, understanding in vitro how these chemicals produce damage to the DNA, or in mice. Mice are a good system to study chronic effects because you can study exposure over the lifetime. And we found effects in terms of carcinogenesis at various organs like liver, lung, skin, in the immune system, and also in terms of behavior. And also some studies with humans, actually, where volunteers are breathing in third-hand smoke from a special chamber we have in UCSF, and finding that there is some acute effect in terms of gene expressions in the nasal epithelium. And this is a very recent study from this year. So finally, I want to say one word about policy. There is already activity in terms of third-hand smoke at the state level. Both the state of California and 14 other states have implemented bans on home daycare centers over the past few years. In the case of California, our work actually was used as part of the rationale for that, for those measures. And as a, we are trying to expand on that by very recently, about a year ago, we developed this resource center, which is not just a website. We have a very nice website, actually, thirdhandsmoke.org, but also it became very active in social media and with the idea of contributing to research translation. So trying to bring the findings of this consortium to the general public, to stakeholders that have really a particular need or particular situations related with third-hand smoke, whether it's housing, real estate, in the hospitality industry, etc. And we are targeting some policy directions in terms of public housing, consumer protection, and looking at loopholes on the current smoke legislation. In terms of where this is going, future direction, the consortium continues, and in our lab, we're very glad that we continue working on this, in a way leveraging the work that as a federal organization we do with funding from, in this case, the state of California, but possibly also other federal funding agencies that are currently being starting to fund this work, like HUD and the NIH. Also, last word, this research is going really beyond this consortium, and I'm listing here just a few organizations, universities that are actively working on various aspects of third-hand smoke, including indoor chemistry, and some of these groups are supported by the Sloan Foundation to do really wonderful work in terms of understanding this complex chemistry. And final word on vaping. Clearly, all what I described today is about cigarette smoke, but many questions arise in terms of, okay, what about vaping? Are we going to see similar chemistry if people vape instead of smoke? We can talk about that maybe in the questions. That would be a little too much for now. So thank you very much. I want to finish by acknowledging a lot of people involved in all of this, in our group, first row, and the consortium in the rest of the slide, and of course our funding agency in the state of California, Tobacco-Related Diseases Research Program. So thanks very much.
Next, I'd like to introduce Dr. Rich Coursey. He is the Dean of the College of Engineering and Computer Science at Portland State University in Oregon. And he's actually been working on indoor air research for about 30 years. and that includes the interactions of volatile organic compounds and materials. He's led a very unique NSF IGERT program that educates students in indoor air chemistry, and he's currently the president of the Academy of Fellows for the International Society of Indoor Air and Climate. Rich.
30 years. I guess I'm the old person up here, I guess. So thanks for coming out during lunch. I appreciate that very much. I started my career a long time ago, and mostly doing outdoor air pollution research back in the late 1980s, early 1990s. I got interested in indoor air quality in the 1990s for two main reasons. Number one was the recognition of how much time we as Americans spend indoors. So the average American lives to be about 79 years old. We spend 70 of our 79 years, almost 70 of our 79 years, domiciled inside of buildings. Think about that. That's a greater fraction of time than whales spend submerged below the surface of the ocean. We're indoor creatures, and we spend 54 of our 79 years inside of our own homes. So when it comes to being exposed to things, our home is a place where we get a lot of exposure to air pollution and other things. So my research focus has been for the last 15 years or so on how pollutants interact with indoor materials. When I walk into a room like this, I see carpet, I see ceiling tile, I see latex paint. I also see polyurethane foam in your chairs that you're sitting on. I see your clothes, I see your skin oils, I see your hair, and I see some very supersized cookies that some of you have been eating. And I'll come back to food and polyurethane foam in just a moment. Both potentially very important indoor materials. So why are indoor surfaces important? Well, they're important because they're huge. When you look at the surface area of materials inside of buildings and divide that by the volume of air in a building, that ratio, the surface to volume ratio, is 300 to 1,000 times that ratio outdoors. So pollutants in the indoor environment come in contact with materials a lot more than pollutants do in the outdoor environment. Materials indoors are dramatically different. The latex paint on the walls is different than the skin oils on your face. So they're kind of complex and interesting. They're dynamic, as Nina said. They change over time. They accumulate organic films and dust and water films, et cetera. Materials are emission sources to the indoor environment. They emit bad things to the indoor environment. And as I said, pollutants interact with them. Gaseous pollutants stick to them and then unstick from them, as Hugo was talking about. Adsorption, desorption processes. Particles deposit on surfaces, and when particles deposit on surfaces, the surfaces can actually transform those particles, and then chemical reactions occur between oxidants and surfaces. So I'm going to give you examples of each of those phenomena I just mentioned in the remainder of my talk. My team has done a lot of research on how gaseous pollutants indoors stick to or adsorb to ranges of indoor materials and how quickly they come off. And sometimes they come off in seconds or minutes, sometimes they come off in weeks, sometimes they come off in years. It depends on the material and the pollutant. So what we do is we put materials in We put materials in these little stainless steel chambers. We close up the chamber. We pass high purity air through the chamber, and then we inject a chemical, and we look to see how much of that chemical actually sticks to the material. Then we stop injecting the chemical, and we see how long it takes to come off. So this is for this plot here, which I'll explain in just a moment. It's just for one chemical, but we have these for dozens of chemicals and dozens of different types of materials. The vertical axis, think of that as just the level of pollutant in the air inside the chamber. And then the horizontal axis is the time of exposure, the time at which a material is exposed to this particular pollutant, dichlorobenzene. If there's no sticking to the material, if the chemical is not sticking to the material at all, the data should fall on that solid pink line that you see up at the top. So that's the no stick line, if you will. And the further you are away from that line, the more the pollutant is actually sticking to the material. And so we see here that materials interacting with this pollutant fall into three main categories: those that don't have a lot of stickiness with the material, those that are kind of somewhere in between, and those that adsorb a lot of that particular chemical. And I can talk about all the materials on here for the next 2 hours, which I don't have time to do. So I'm going to focus on that last group. Those where that's the group where a lot of sticking of this particular chemical happens, and that happens to be mostly carpet with polyurethane foam cushion underneath. So we took we took carpet and we looked at it as a system, all the major components, and then dissected the carpet. So you can see nylon fibers here, the polypropylene backing that holds the fibers in place, and the bonded polyurethane cushion underneath the carpet. And we repeated this experiment with the components of the carpet, and what you see on that plot on the right is the exact type of plot that I just explained to you. The pink squares that you see that are close to the no-stick line, those are nylon fibers, and that makes sense. Nylon fibers tend to be stain resistant. They have a chemical on them that causes stuff not to stick to them, and we see very little of this relatively sticky chemical not sticking to nylon fibers. The green triangles you see are the polypropylene backing that holds the fibers in place, so that some of the chemicals sticking to the polypropylene fibers below, polypropylene backing below the fibers. The asterisks are the polypropylene backing plus the fibers, and then if you move down to that next group of curves, those are the actual carpet system, all the pieces put together, and that last dashed blue line is the polyurethane foam cushion exposed by itself with nothing on top of it. The moral of this story is that polyurethane foam collects a lot of stuff in indoor environments. Your sofa cushion, the cushions in the seats that you're sitting on right now, carpet cushions, your pillow cushion, tend to be reservoirs of chemicals, and oftentimes chemicals get stored in polyurethane foam for a relatively long time. So if you want to know what your house has been exposed to, check out the polyurethane foam, especially if you're buying a new home. All right, so chemicals also desorb from materials, and my team has done some research, and a lot more of this research needs to be done, on mechanisms that accelerate desorption of things like methamphetamine from indoor materials and meth-contaminated homes. This is not methamphetamine, but what we've done is to go into homes and we actually humidify bedrooms or we humidify living rooms, and we measure the amount of pollutants in the air in that space before we humidify and after we humidify, right? And what we can see is that before we humidify, the blue bars on the right are considerably lower amount of, and just think of this as the amount of stuff in the air, right? It's a measure of the total mass of pollutants in the air. And the red bars are after we humidify in this particular house. And we've done this for 6 homes, 13 events, and every single time when we increase the relative humidity within reasonable bounds, 40% to 60%, 45% to 60%, we see gushes of chemicals coming off of materials into the indoor space. This is fascinating. It suggests that when you have RH cycling in a house, that the people in the house are going to be exposed to gushes of chemicals whenever the relative humidity increases. And that's an area of research that we need to do a lot more of. Has impacts potentially on damp buildings. With energy savings, we're trying to readjust thermostats now that change the cycling of the HVAC system, which might mean higher periods of relative humidity in certain parts of the country, which means exposure to more chemicals. We don't understand the mechanisms, which is interesting. We need more research in that. But think about how we might optimize this. Imagine going into a school classroom, and before the kids get there every day, we humidify the heck out of the classroom. We desorb chemicals off of the materials. And by the way, all the chemicals we identify are things not associated with the surfaces themselves, or things that have stuck to the surfaces. They're fragrances and pesticides and things like that. Imagine humidifying and then flushing out a classroom to get rid of the contaminants before kids get to school every day. You know, can we optimize this process? We can do it if we understand it better. All right, particles, as you know, dust deposits on surfaces, and when dust deposits on surfaces, they tend to lie in this very thin boundary layer, the skin of an apple next to the surface. And anything that's coming out of that material tends to have a very high concentration, a very high level of stuff coming out of the material in that thin boundary layer. So the dust that's sitting on a piece of material is going to actually accumulate whatever's coming out of the material. And that can be particularly important if there are things like flame retardants or plasticizers that are endocrine disrupting chemicals that accumulate in the dust, and then somebody walks across the dust or a child crawls across the dust and it's resuspended and you breathe it. That becomes a mechanism for really getting those concentrated pollutants into your lungs. So the test house, again, which you've already heard about, I won't explain it, but the flooring of the test house is filled with a chemical called butylbenzyl phthalate. It's a plasticizer. It is an endocrine disrupting chemical, and it's the only material in the test house that has butylbenzyl phthalate in it. So one of my colleagues collected dust samples from all the surfaces in the test house, including the flooring in the test house, and analyzed that dust for butylbenzyl phthalate. The red bars that you see here are dust collected off the floor that contain butylbenzyl phthalate. The green bars are dust collected out of all the other surfaces in the house. So you can see how badly the dust is contaminated that actually falls on the floor that's filled with butylbenzyl phthalate, and that's a common plasticizer in vinyl flooring. Finally, chemical reactions occur on surfaces. I've done a lot of research on ozone chemistry on indoor surfaces. When ozone reacts with indoor materials, that's a good thing. That's why ozone levels are lower indoors than outdoors, and we know ozone's a harmful chemical. But at the same time, when ozone chemically reacts with surfaces, you always form reaction products. Lots of reaction products of different nature, right? And Barbara mentioned that we don't know the toxicological effects of a lot of those kinds of chemicals. We just know that we form a lot of them. So one of Barb's colleagues, Glenn Morrison at the University of North Carolina, and I came up with this concept a few years ago called passive removal materials. We said, what if we could redesign indoor environments so that we have materials that remove lots of ozone, which is a good thing, and produce minimal reaction products? We'd like to fill buildings with those kinds of chemicals so we're not exposed to those reaction products. And we've tested over 32 different materials. You see 4 or 5 in the upper right-hand corner here that are particularly good at what I just said, removing ozone and not forming reaction products. And our very first experiment, what we did is we took a ceiling tile in our test house at the University of Texas, a ceiling fan, and we created for $2 some activated carbon cloth slippers that fit over the fan blades in our test house. Activated carbon is great at removing ozone and doesn't form any reaction products. And you can see by the result in the lower right, the middle orange bar is a measure of the rate of ozone removal in the house. Just by putting $2 worth of activated carbon on fan blades, we removed a huge amount of ozone in our test house without producing any additional reaction products. Oops, I keep doing that. And finally, more recently, so the other end of the research, starting with activated carbon, clay paints and clay plasters have this magic property. If you get the right kind of clay that's got lots of kaolinite in it, an aluminosilicate compound mineral, you can catalytically decompose ozone without forming any reaction products. And we find certain clay plasters and clay paints that have lots of kaolinite in them very, very effective at removing ozone in indoor environments. Sustained high removals, minimal reaction products. They also remove organic acids that are in the air, which is great. Organic acids can degrade works of art, for example, buffers water vapor, and we've done studies with human panels to show that human panelists actually feel like the air is cleaner when it's been exposed to clay plaster or clay paint. So my takeaway points are listed here. I'm not going to read all of them. The most important are the last 2, which I think there are opportunities to rethink the use of indoor materials as being beneficial for us instead of enemies, right? And a lot of important research is still to be done. This is a wide open field, and I think over the next decade or so, you're going to see a lot of advances if we focus on this field that improve the healthiness of buildings. That's it. Thanks.
So thank you. I'm going to give you a chance to ask some questions. And I also wanted you to know that tomorrow there's a full day of talks about indoor air chemistry. There's at the AAAS building, there's a symposium on the chemistry of indoor environments, and it's sponsored by the Sloan Foundation. So you're all welcome to come to that. Do you have, and when you ask your questions, we'd love to know your name and what office you're from. So questions? To any of our panelists? Yes.
My name is Christoph. I am an intern with the School of Practices office, representing the practices. Last year, 2018, the World Health Organization attributed about 4 million deaths to indoor air pollution due to indoor combustion of organic materials. However, organic materials seem to, on Dr. Corsi's slides, be less absorbent, or at least by wood and apples, the few odd examples mentioned there, seem to be less, let's say, detrimental to health than a lot of these plastics and whatnot, inorganic plastics. Is that generally a trend that organic materials, say the aromatics in cedar wood, are less harmful to our health, or am I just imagining that?
I can take that if you want. So in the World Health Organization, what they're talking about there is combustion of biomass fuels in homes. And what Rich is talking about is material like activated carbon that just sits there and adsorbs materials. I don't know, would you, products of combustion are often not very healthy to be breathing.
Yeah, I was going to add that. I think that when you look at the sort of spectrum of indoor pollution, if you don't properly vent while you're cooking, and this, I'll kick this back to Nina in a moment, you know, combustion of natural gas creates pollutants we're exposed to that we know are harmful. Nitrogen dioxide, for example, in indoor environments, particulate matter that Nina mentioned. It's not to the same scale as cook stoves in, you know, in Asia, that type of thing. But it's still, from our perspective, it's a really important source from a health standpoint, and the research actually bears that out. I don't know if, Nina, you want to add to that.
I think you guys covered it pretty well. So when we're talking about organic matter, there's so much there, and I think those are two very different things. So the organic matter that's present in our homes as a building material, unless there's a fire, that's not going to become a source of particles. But then the World Health Organization study was really talking about combustion of biomass. So using wood or coal or other kinds. Some people use dung, and they're burning those materials for cooking, and that leads to very, very high emissions of particulate matter.
Now, often not ventilated very well. And so especially women and children spend a lot of time indoors in a very smoky environment, breathing those products of combustion. Other questions? Yes.
Plaster about this, and I was really impressed with the Thirdhand research strategy or roadmap. Is that something that was instigated by a federal scientific agency, or is that something that you all organically developed on your own?
No, actually, the study was. Yeah, this was a study that it was essentially carried out in California by 8 different research groups, all of them funded by the state. The state of California has an interesting funding mechanisms for tobacco-related, it's called Tobacco-Related Diseases Research Program, and it goes on one side covering the health side, but also the research like what we do in terms of chemistry and exposure. And that fund is, that program is funded directly from the tax on tobacco products. I'm not aware of other states having a similar program like that. In our case, because we are a federal organization, the lab is Department of Energy laboratory, what we do is, in a way, we can carry out that research by leveraging the resources from the DOE and LBNL. For example, just to give you an example, some of the measurements I show here were done at a big facility we have that is called the Advanced Light Source. It's a synchrotron that where we do research both in-house, but also mostly we host researchers from around the world to do really cutting-edge studies. So that's one of an example in which you know, our research is both benefiting from being in a federal organization and also the state resources.
Other questions? Yes.
Can you talk a little bit about...
Your name and...
Oh, yeah, I'm sorry. Seth Stokes from Senator Feinstein's office on the intern. Let's see. Yeah, so could you talk a little bit more about how some of these indoor pollutants affect like worker productivity, maybe like office buildings?
Sure. You want to take that? Okay. Productivity is is a field that has been studied for a long time. And we are learning more and more about, let's say, traditionally, I think productivity was defined in terms of, or quantified in terms of, for example, typing mistakes or more mechanical effects. And in order to get to that, you need to have really poor air quality levels, which is often not the case in most cases. So what we are learning now through relatively newer studies is that much lower levels of pollution that we thought historically that were not a problem. I'm talking in this case about carbon dioxide. So levels of carbon dioxide in buildings that are at levels that we possibly could have in this room or in any classroom where you have a large number of students. Some of these are new studies. It's research that has to really be confirmed and validated by more numerous studies. But what it's showing is that you start perceiving some effects in what is called cognitive performance, and that is measured indirectly through, for example, through a software system where people can be performing simulated tasks, and the software can quantify how those tasks are done and give you a number out of that. So you can even assess, for example, the focus or how you use information. These are really difficult things to measure. There is a recent study that was led by Harvard about a year ago in which something similar was done with pilots running airplane pilots running a simulator. And in that case, the evaluation was done by an FAA-trained person that would sort of rate and quantify the maneuvers and the number of mistakes that were done. And also in that case, there was an effect with the CO2 level in the range of values that we typically have in buildings. So that is, I think, growing evidence that there is an effect, there is something there. It's another example, I think, that we can mention here about how much we don't know yet about the effects of indoor air quality on not just our health, which of course is bad when you get to a health effect, but even if you don't get sick, you can even have important effect in terms of productivity measured in different ways. I think about students in a classroom. That is a situation where you really want students to be creative and engaged and paying attention, etc. So this is a really, really important problem to focus on.
Yeah. If I can add a little bit to that, just coming from the studies performed outdoors, large epidemiological studies that look at populations and their exposure to outdoor pollutants. We don't really have that huge body of knowledge for indoors, but there have been studies showing that concentrations of particulate matter as they go up, there are more subtle health effects, like what Hugo was saying, related to the aging of your brain, stress levels, anxiety, and things like that, that maybe 10, 20 years ago we wouldn't even think about. We would think about mortality rates, right? But now we're getting to the point where we can discern these more subtle health effects related to really quality of life, and we are finding a link between air pollution exposure and quality of life.
Another question over here.
So I'm Sean with AAAS. On a personal level, are there things that you, as scientists who do this kind of research, would you say I don't like having in my home that you would want to offer as someone who has 2 young children?
And so I'm going to repeat the question so we get it in the recording, but the question is, on a personal level, are there things that you would prefer not to have in your home, especially if you had young children?
So the last part of that question is a really important part. When you reach a certain age, I get asked this a lot when I give presentations. When you get to my age, I don't worry about being exposed to a lot of things anymore. That's one of the benefits of getting older.
You're not that old.
But I am concerned about young couples that are thinking about starting a family or that are pregnant or have young children in the home. I think that's the most important part of life, and that's where we don't want to have a fetus or children exposed to things like endocrine disrupting chemicals, various flame retardants, plasticizers, et cetera. I think the other issue is cooking again, and I know at least in Texas, where I used to live until a year ago, a lot of homes were constructed without exhaust vents on stove hoods. So they were just basically recirculating grease traps that basically just blew all the gases from your gas stove and particles, et cetera, back in your face. So it's not just what you're exposed to, it's how you're exposed. And so I would be concerned about a house that doesn't have an exhaust vent over a stove in the house. But I think where you are in life is important, and the last part of that question was really critical, is if you have children in the house. Don't burn scented candles. That's another thing I would say. So scented candles particularly generate a lot of fine particulate matter and can have polycyclic aromatic hydrocarbons in them. I go into a lot of young people's homes that do have children, and you see scented candles all over the place, right? So That's another source I would tell people not to use.
I've stopped using Teflon-coated pans. I've gone back to the cast iron and the plain metal pans. And we take our shoes off when we come indoors, so we're not tracking in old paint dust from, in the dirt around our house. Others?
God, where to begin? So I'm actually expecting a baby. I'm 6 months pregnant, so I've been thinking about that a lot. There is a lot that you can do, but there's a lot that you really can't avoid. For example, my office building was painted not 3 weeks ago, like the first week of classes. We're back on campus, and then they decide to paint my hallway, and I was pretty upset because I had meetings and I couldn't just skip work and go home, right? Even though I understand that SVOCs are emitted during painting and I should be limiting my exposure. Another thing that I did is, we have a room for the baby in the house. We did not paint that room because I see a lot of ads and I see a lot of, pregnant women painting the baby's room. Everybody wants the nursery with the decorations, and that was something I was adamant against. So I try to limit exposures, and I will reinforce the point that Rich made about combustion in general. We know a lot of research, as mentioned before, about exposure in developing countries where we're using these really inefficient combustion heat sources for cooking. Well, we're in a developed country. I'm sure maybe some of us will use a wood-burning stove at home, but that's really rare. Usually what we have is natural gas burning, and then there are the things you do by choice, which is the burning of candles of any kind, burning of incense and things like that, burning of sage because whatever reason. I try to avoid any kind of combustion source, especially the optional ones in my home, because I know they emit particulate matter of different sizes, and that has a detrimental health effect.
Question?
Can I just one brief, very briefly on third-hand smoke? Clearly, children and small children is a particular concern because clearly the contact with carpet, the contact with surfaces in general, children, especially in the first few months, don't leave the house very much, so the exposure is also a function of how much time they are there. There is also the issue of mouthing objects, everything goes to the mouth. So it's not just dermal uptake of contaminants, it's also ingestion, which is particularly important for children. That is true for smoke, it's also true for all the other semi-volatile chemicals.
Question in the back.
Ken Film with the Congressional GIS caucus. We focus a lot on people chemistry and how people impact indoors. When you add pets to the equation, what measurements or what science is occurring there? Because we have pets as companions, support animals, rescue animals. So there's an interaction or measurement between pets and people.
So the question is about pets indoors and what they bring.
The microphone just got passed to me because I guess I'm the dog person here.
Yes.
Big dog lover. So issues with pets, right? Pets, if they're indoor-outdoor pets, and if there's pesticides outside, they're going to track in pesticides on their paws and on their fur. They're going to roll on the grass and bring pesticides in that way. If you have an indoor-outdoor pet, it's best to minimize the use of pesticides in the yard that the pet's in. That's been documented. If it's a dog, the dander is not as bad as if it's a cat in general from an allergic standpoint, but still there's dust associated with the dander, and that dust, as I said, can accumulate other things and be resuspended. I'm a dog person, and I'm old enough that I don't worry about all those things again, but that's my comment on indoor-outdoor pets.
But I'm a cat person,
Yeah, okay.
just for the record. Other questions? Yes.
Hi, Mel Peppers with House Energy and Commerce. I'm not surprised when I see the slides of funding. That's like a hodgepodge. And I was a little surprised with one, especially in the tobacco, that there's only 2 federal agencies, HUD and NIH. Can you talk a little bit about what policymakers can be doing and federal agencies to support the science, and then vice versa, how science can inform policy? And thank you for the shout out of supporting epidemiology that's taken a bit of a hit for different reasons. But if you could comment on that, what advice do you have for policymakers?
So the question is about what advice we have for policy. And I'm going to turn it over to these guys, but I did want to say that there's a lot left to learn about outdoor chemistry, but there's been a lot more research in outdoor air, and it's probably that there's a regulatory authority that is responsible for outdoor air, keeping outdoor air healthy. That's the EPA, and there is no for residences, for homes, there is no regulatory authority. But there are several federal agencies that do research on indoor air and who make policy decisions that impact indoor air. And some of them are probably in the room today, or they will be tomorrow. So let me turn it over.
Thank you. With respect to tobacco in particular, there is an important framework that is now mostly covered by the FDA and the research done in association with the NIH addressing tobacco products. And that is, if you want, the impact of the tobacco products, and especially the new tobacco products, on users. So what we are describing here is what happens after the products are used in the environment. And as far as I understand, the FDA does not cover that. So that's not their mission. That's not what's on the 2009 Tobacco and Family, I forgot the name of the bill, the 2009 bill that gave FDA authority over tobacco products. The agencies I mentioned, this is very recent development. So it's HAD, I think, was maybe 3-4 years ago, and NIH even more recent. I think it's NIHS, the institute in particular, that is started. This is just 2 cases that I know, because the PI, Professor Matt, is in our consortium, that we were really happy to see that for the first time we're starting to break into this. But clearly you can find in other agencies very relevant questions that could be addressed in terms of third-hand smoke, but I think broadly speaking about indoor pollutants. And that is one of the reasons I think we're having all these conversations is precisely to understand what are the various problems that could be addressed and how. So thanks for the question.
I think that the topic kind of falls in between several agencies. So
Right, I was just going to make that point. Indoor air quality, certainly indoor chemistry, spans a lot of different things, right? And my experience has been oftentimes NIH and NSF may have specific things they want to work on. They're not talking to one another, right? So I'll go to NSF and say, I'm interested in indoor air quality, and they'll say, that's a health issue, go talk to NIH. And you go to NIH and they say, you're an engineer, go back and talk to NSF. And I think they're, bridging agencies that have different interests but around the same subject is something that's needed, whether it be HUD, NSF, NIH, EPA, GSA, DOE, would be a very welcome policy change than the sort of siloed approach that's been used in the past, where we all try to find the right place to figure out where we can get funding for our specific interests, when really it's the field is really an integrated field. What we do on the energy side affects what happens on the chemistry side, affects what happens on the health side.
What happened to Rich has happened to me too. So I just wanted to stress that a little bit more. It's particularly interesting to be in the field of exposure science, so trying to understand what people are exposed to, because for NIH, I'm not investigating the health effects, I'm just saying what's coming into our bodies. So for them, it's not of interest. But then if we go to NSF, they'll say, no, that's NIH. So I wanted to agree with that.
Can I follow up with one thing that Nina said a little while ago, and that was related to her exposure to paint at work. This is something that bugs the heck out of me. So latex paints used to have a small group of volatile organic compounds in them that by every account, every toxicological study caused no health problems at all, right? But they were volatile organic compounds, and people wanted no VOC or low VOC paints, primarily because of concerns regarding those VOCs getting outdoors and producing ozone, right? So the concern was that. But they were of no concern from a health standpoint indoors. In response to that concern, we've now replaced those benign volatile organic compounds in paint with semi-volatile organic compounds, some of which we know are endocrine disrupting chemicals. So in response to trying to generate low VOC paints or no VOC paints to protect the outdoor atmosphere, we've just made buildings a lot worse, especially for people like Nina, who's expecting a child. And that's, I think, based upon a lack of science, a lack of knowledge, and I think it's really reflective of the fact that this field just needs a lot more research and a lot more public education and policy, education of policymakers. It was just a bad decision, and it drives me nuts every time I hear the word paint.
So for the last point, I'd like to bring Annette up.
And we're organizing the symposium tomorrow. We have 3 of the speakers, well, 4 of the speakers, because Barb's also speaking. All are speaking tomorrow, but we also have some speakers on some different topics as well. Alan Goldstein will be speaking about a comparison between indoor and outdoor air. We're going to have people speaking about long-range transportation of these indoor pollution particles all the way to the Arctic. We're going to be having somebody who is going to be speaking about cook stoves, about human emissions and how that interacts. But also an interesting topic is going to be about how indoor air pollution affects outdoor pollution. So if you want to learn more, you can join us tomorrow either at our headquarters, or we also are doing a webcast. And you can come up to me for more information. And there's also the brochure for the symposium is outside on the table. Hopefully there's still some outside. But I definitely want to thank all of our speakers for flying here, coming here to present today and discuss today. And if you have any questions afterwards, we'll still be around for a few minutes. And I think that's it. Anything else, Sean? Okay, great. And thanks to Sean Gallagher at AAAS for helping organize this here. Thank you.